So what did we do last time? For blue. Last time we sort of we talked about, so we really got into optimal control, right? So we talked about deterministic optimal control and the fact that maybe unlike some other contexts you've seen before, the solutions to these deterministic optimal control problems is not a feedback policy. It's actually just an open loop trajectory. And we'll get into the feedback policy stuff in a little bit, but that's kind of an interesting nugget, right? With no noise, the answer is just an open loop trajectory because it rolls out the same every time. And then we sort of did Pontryagin, right? We talked about for us, the minimum principle, but if you like to maximize rewards instead, you can call it the maximum principle. I think the original Pontryagin work back in the 50s was actually maximum. They were maximizing back then, but it's sort of whatever. Take your pick. So we did that, right? And we derived those things explicitly in discrete time where they're just versions of the KKT conditions. And then I kind of threw at you the continuous time versions, which are identical. They just replace the Ks with dots, right? And you get ODE versions of those things. And we talked through how that defines this funky forward-backward shooting kind of setup where you have to roll the dynamics out forward in time, but then to compute those co-states or lambdas, and to compute the controls, that's actually a backward process, backward in time. And so generally we start out with initial conditions on the state and terminal conditions on the lambdas based on our terminal cost that we write down. And then we have to like do some weird kind of forward backward stuff to get it to converge. And we finished up by kind of defining by talking about single shooting, right? Or indirect shooting, we'll call it. And we, in particular, demoed this on the LQR problem, right? And that was kind of our entry point into kind of what we're going to do today, which is dig way deeper into LQR. So first, any questions on any of that stuff from last time? It comes straight, it's literally at time n, lambda is equal to the gradient of the terminal cost. So if you have your terminal cost L sub n, literally lambda n is dL sub n dx. It's just a gradient, and that's it. Cool. All right. So what are we gonna do today? So today we're really gonna dig into LQR. So we're gonna do kind of LQR recap from last time, like get back into it, and then we're gonna talk about how to sort of interpret this as a QP. So we've already seen QPs. We're going to show you how LQR is just a QP, and we're going to solve it that way and talk about that. Then we're going to, from there, dig into the guts of that QP and look at it at a kind of more granular level and play some math tricks and come out with this interesting recursive solution to that QP called the Riccati recursion. Who's heard of that before? Decent number of you. Okay. Where have you seen that before? Like other controls class or from LQR? Yeah, somewhere. Cool. Okay. And then maybe get into some like kind of extra little LQR related nuggets at the end, hopefully. Okay, so any question about anything before we get into it? Okay, cool. So first thing is just a recap of what that LQR problem looks like. As we kind of just threw it at you at the end last time. So we're going to do everything in discrete time. And so the LQR problem is a trajectory optimization problem, aka deterministic optimal control problem, where we're optimizing over states from 1 to n, those x's, used from 1 to n minus 1. And we talked about how you end up with one fewer control because at the last time step, you just end up where you end up, and that's x sub n, and there's no more control moves. So you're done. So then we write this cost function down as a sum over the time steps from 1 to n minus 1, where you have, here's the stage cost. It's xk transpose, and in general, these can have subscripts on them, right? They can vary in time. Yeah.
Like how you don't define the final control? Should we define the initial state? Is that given to us? Or?
Yeah, generally speaking, the initial state's going to be given to you. You're saying I'm starting here, and I'm trying to minimize this cost, which may include some goal state, right? And typically in this context, you would encode the goal in that terminal cost. It's possible to add terminal constraints to these problems also. Like if you said, I really need to get to this terminal like goal state as a hard constraint, you can do that as well. That doesn't fit into the LQR problem, though. That's a sort of separate idea that we'll get into. So in this case, if you wanted that, you would put it into a big terminal cost.
The final state, I understand that we put it on final cost, but the initial state, we are not minimizing over it, really, given that.
Yeah, that's the idea. Yep. I mean, there's many variations on this theme. There's a lot, but I would say in practice, that's typically what's happening. You're given a state. You are where you are. You get it from your state estimate or whatever, and you're plugging that in. And then, yeah, this is looking forward in time from there, right? And we'll make this a lot more concrete in a minute. We're going to write this stuff down, and that will come up explicitly. Okay, so that's our cost function. We got a stage cost inside the sum there, and then we got this terminal cost that's just a function of xn at the end. Then we've got linear dynamics, which in general can also be time varying. So we can have a sub k that changes as a function of k, and then b sub k that changes as a function of k. And then to make this problem well posed, we talked about it for QPs, if we want that to be convex, we need the Hessian matrix in there to be generally positive definite. So it turns out for the LQR problem, we specifically need the Q matrices, the state cost matrices. Those guys all have to be positive semi-definite. So in general, they can be 0 too, right? Or you could have some of them 0. You could not care about the cost on certain states, and that's legal. The problem's still well posed. But you absolutely have to have the control cost, the R matrix. That has to be strictly positive definite. We can't have zeros in there, because if we did, there's no cost at all on control effort. So if you have a cost on the states where you say, oh, I want to get to this goal or whatever, you put 0 cost on the controls. The optimal thing is to slam the controls as big as you want, right? So in general, problems that have like a 0R or whatever, the solutions will be unbounded, like the controls will just go to infinity. So in order to make the problem well posed, you have to have a strictly positive definite R weight in there. Not allowed to have zeros there. What happens? Yeah.
If you don't care about how much work you're doing, but you have like caps on form.
Yeah, that's a little bit different. You can absolutely do that.
Yeah.
That would be then inequalities on the U's. Totally legal, and we're going to get to that in a couple lectures. It's not LQR anymore, though. So LQR is specifically this problem where the only constraints are the dynamics. You're not allowed to have any other constraints. And you'll see why, like today and next time, like what's going on there. This is a very particular problem. And it's nice, and we do it this way, and we specifically spend a lot of time on this because it's one of these rare gems where there's a closed form solution. And we can actually get a lot of insight and leverage that closed form solution in a ton of different areas. As soon as you start adding other constraints like those, it's no longer got a closed form solution. You have to solve it numerically. That's fine. We do it, and we're going to do it here. But it doesn't have the clean closed form solution anymore. So that's kind of the message there. And again, we care about this because you can use it as a local approximation of almost every control problem, right? So if you zoom in locally, if you do like first, second order Taylor expansion of any deterministic optimal control problem, this is what you're going to get as like the low order Taylor expansion of any other optimal control problem. So in some sense, it's like the simple harmonic oscillator of control, right? When you take physics, you get some nonlinear dynamics, but if you zoom in locally, you can like quadraticize the potential or whatever, and linearize whatever, and you'll get like a simple harmonic oscillator, right? That's the kind of the idea here. Any optimal control problem, if you zoom in closely, it looks like this. So this is like super, super useful. Cool. All right. And we said a bunch of stuff about this last time. Oh, the other thing we did last time that I wanted to just highlight, we did at the end, right? I showed you this example of a double integrator. So I actually wanted to write that out and talk through it real quick so that we're clear, because I kind of glossed over it because we were getting low on time. So this is called the double integrator. And this is going to be our kind of prototype system to test this stuff on today as well. So it's worth just talking for a second about it. Double integrator is an EE word. This is coming from electrical engineering. But it's, it's a very, very common thing. If I were thinking about it as a mechanical system, I'd think about like a brick slotting on frictionless ice or something like this. And the dynamics of this guy in continuous time, if I were to write them out as a linear system, we've got a state vector with a position and a velocity. So Q and Q dot, if Q is your position coordinates, and we're just going to do it in 1D. So Q is a scalar, Q dot's a scalar. So X dot then is Q dot, Q double dot. And then the dynamics here, it's literally just Q dot up top equals Q dot from downstairs on the original state vector. So that's what the A matrix looks like. And then the input is a force. So I'm just, using normalized units here. So force equals acceleration, whatever, right? And that's going to look like this. So just to kind of, label this all, our input here is a scalar force. The state vector X has a velocity and a position. And this Q double dot is the acceleration, right? So this is just F equals ma, and I'm just like writing it out this way, right? And then I can discretize this, right? And write it in discrete time. So just as a note, right? Think of this as like a sliding brick. Sliding on ice, no friction. Okay, and then in discrete time, this is going to look like xk plus 1 equals, and it turns out this one, we've talked a little bit about how I go back and forth between continuous and discrete. You can use Runge-Kutta, blah, blah, blah. So in general, that's what you do here. You can just throw this into Runge-Kutta. It turns out in this case, it's a really, really simple system, and you can write down the exact discrete time version in closed form. So I'll go ahead and do that. It looks like this, where h is the time step. And this is like kind of super obvious stuff, right? You can figure this out. And then the B, you've got like an h down here. And it turns out, right, if I integrate acceleration, I get a 1/2 h squared in the position, right? Okay. And then this h is the time step, right? And this is going to be, for our purposes, right, we're going to do everything in discrete time. So this is our A. And this is like xk. And this is our B. Cool? All good? No, I mean, you would get this from RK4, but I'm just writing it out in closed form because I can, right? If it were like a gnarlier nonlinear system, I wouldn't be able to do this in closed form. So I would use RK4, which is ultimately giving you an approximation of this, right? It's giving you a fourth order accurate in the Taylor expansion approximation. This thing's super nice and chill. And in fact, if I look at what's in the A's and B's, what's the highest order it goes to second order, right? So if I did this with RK4, I'd get the exact answer because RK4 is accurate to fourth order. So like to machine precision, I would get the exact answer here with RK4. I don't need to do RK4 here because I can just eyeball this and write it down because it's super, super simple, right? So just, fun fact, you can write this down in closed form. There it is. If you wanted to, you could use RK4. You could also use the EXP matrix exponential to get this in Julia, MATLAB, Python, whatever. But yeah, that's it. Super easy. Cool. Okay, so that's that. So we did this last time, right? And we'll do it again. And we'll revisit this in a sec. Maybe just as a refresher, we'll do that real quick. So we did the Pontryagin thing last time, right? And we had this written down here. There's what I just wrote down, right, with the A's and B's. We saw this last time. And we're setting up a really simple problem with Q's and R's where I'm penalizing, identity on the Q's and 0.1 on the controls. And implicitly here, right, I'm penalizing deviations of the states and controls from 0. So what the control is going to try to do is drive the system to the origin, both and to be stationary at the origin, right? So 0 velocity, 0 position. And then it's also trying to, minimize control effort as part of this. It's trying to drive the controls to 0 as well. There's the cost, blah, blah, blah. We do a rollout. We do this backward pass kind of thing with the shooting, right? Which is, again, equivalent to back propagation in a neural net. It's going backwards, and these lambdas and everything are really just getting gradients with respect to the U's. We're doing gradient descent. And then just kind of looking at this, right, it gets us where we want to go. But note the, lots of iterations, and it kind of sucks in various ways. And that's what the controls look like, right? So if you think about this for a sec, we're starting it out at x equals 1. So the initial controls are super negative, i.e. they're pushing us to the left, back toward the origin. And then over here, we start to, when this crosses, right, we're hitting the brakes over here. So this is trying to slow us down. So we kind of like coast in and don't overshoot. Cool. Okay, so this from last time. All good there. So now what we're going to do is we're going to like dig into this problem a little more, and we're going to try to pose this as a QP now. And we'll like compare that to what we saw before with that shooting stuff. So here we go, LQR as a QP. So here's what we're going to do. As you asked before, we're going to assume X1 initial state or whatever is given. And in practice, you're going to get this out of a state estimator or whatever, right? Is given. So in particular, in optimization lingo, that means it's not a decision variable. We're not optimizing over X1, right? And I really need to figure out how to turn off the auto spell check red underlines in this thing. It's just kind of annoying. Okay, so what we're going to do now is we're going to write this whole LQR problem as a big QP. So we're going to define some stuff. The first thing we're going to define is a vector we're going to call Z, which is just a stack up of all the variables, all the decision variables in the LQR problem. So we're going to stack it up into one big vector. So in particular, X1's not in there. So we're going to start at U1. So we got U1, then X2, then U2, then X3, blah, 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 all the way to Xn. So we're going to stack up all the variables in the LQR problem over the time horizon, just alternating X's and U's, big vector. Cool. Okay. Next move is we're going to take the cost function from LQR and we're going to write it as one big matrix such that it sort of gives us that whole sum over time in terms of the Z vector. So that's going to look like the following. And define this big H matrix. And can anyone tell me what this is going to look like? It's going to be block diagonal, and the diagonals are going to be what? Alternating like R's and Q's, right? So the first one's going to be, you know, U1 transpose R1, you know, U1, that kind of thing. And then Q, then R, then Q until we get to Qn at the bottom, right? Cool. So that's going to let us write this entire, you know, sum over K cost function as one big quadratic form, one big sort of, you know, Z transpose H, Z kind of thing. So we're going to start up here with R1, then Q2, then R2, dot, 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 all the way to Qn. And then everything else, the diagonal, the block diagonal is going to be 0. And we're doing this such that that whole cost function from before is now just 1/2 Z transpose H Z. Does everyone see that? Any questions about that? Okay, cool. So that's the cost function. So now I need to get the dynamics in there, the dynamics constraints. So I'm going to basically try to follow the same playbook. I'm going to try to write down, remember these constraints, this is a set of constraints for all K, right? So I need to basically stack up that xk plus 1 equals axk plus buk thing into one giant matrix equation in terms of the Z vector, right? Make sense? So we're going to now do the same trick and we're going to define a big matrix, capital C, and a big vector, little d, to like encode that in terms of our Z now. So this is going to look like the following. So remember that we are not including X1 in Z, but it still has to show up in that first dynamics constraint. So the first row, this is a little different. So let me write some, so we'll kind of like cartoon this. And let me write some stuff over here first. So we're going to have U1, X2, U2, dot, dot, dot to Xn in here. And the first line is going to be, if I go back up here, right, I need to write X2 equals AX1 plus BU1. X1 is not in there, so X1 is going to have to go on the right-hand side in the D. And I'm just rearranging stuff so that I can write that constraint in this form. So in particular, here's how that first row is going to look. So I've got the U1 in there. So I'm going to do BU1. So I guess this is B1. And then I'm going to move the X2 over to the left-hand side. So I'm going to get minus X2. So then I'm going to have a minus I here. And then I'm going to put the AX1 term on the right-hand side in the D. So that's going to be minus A1 X1 over there. Remember, not a decision variable. I just compute that, right? And then after that, it's super easy. And it just has this repeating pattern. So it's just A, B minus I for everything else after that, right? So I just move everything over to the right-hand side, and I get like AX2 plus BU2 minus X3 equals 0. So then the rest of this vector on the right is 0 after the first time step. And this thing just looks like, and then the zeros, everything's 0. And then everything here, zeros, you get the idea. And then this whole thing is going to kind of go down, continue down on the block diagonal. So this is 2, right? Get the idea. And then until we get to the last time step, so we got some big dots here all the way down until over here, we're going to get the xn term, same kind of thing. It's going to be a n minus 1, b n minus 1 minus xn. Cool. Does everyone see that? It's just me kind of moving everything over so it looks like, you know, AXK plus BUK minus XK plus 1 equals 0 for all the Ks in one giant matrix, and we write it in terms of our Z. So now this looks like one big linear constraint, C times Z equals D. And I can write it like that. So far, so good. Okay, so now that I've done that, this is just a super vanilla quadratic program, equality constrained quadratic program. I'll show you that. Just a standard QP where we've got min over Z, 1/2 Z transpose H Z, subject to C times Z equals D. Okay, what do you think we're going to do now? I'm going to go solve this QP. So I want to write down KKT conditions, all that good stuff. So the first move is we're going to write down the Lagrangian of this guy. So we're going to have L of Z and lambda. We got to have our Lagrange multiplier for those dynamics constraints. And this is going to be the objective. So that 1/2 Z transpose H Z. And then we're going to grab our lambda in here and just put our CZ minus D equals 0 constraint in there, right? Textbook stuff. We've been doing this for a while now. And so next move, we're going to do KKT conditions. We're going to take gradients of this guy, set them equal to 0. So that looks like grad Z of L first is just going to be HZ. Sorry, did I screw something up? Oh, is it the parentheses in the C looking weird? Yeah, I'll try to fix that. Maybe do no, I don't have the best handwriting. I try. We'll do a square bracket. Is that better? Yeah, sorry about that. Tell me when it's looks stupid. I'm apologies in advance. Okay, so yeah, the grad respect to Z, we're going to get HZ plus C transpose lambda equals 0. And then the grad respect to lambda, we all know what that's going to do. That's just going to give us right back the dynamics constraint there, CZ minus D equals 0. And now we're going to package that up into a nice KKT system, right? A linear system. Super simple. So we've got H C transpose C 0. We got our Z and our lambda. And then on this end, we're going to have 0 and then D. Right, so I just rearranged that stuff and wrote it in the form of like a linear system. Okay, cool. So now we have a QP for the LQR problem, and we can go solve this thing. We can go solve this linear system. First question, how many iterations is it going to take to solve this thing if I do like Newton's method?
1.
Exactly, yeah, trick question. It's a linear system, so this is exact. There's no approximation. I didn't linearize anything. That's it. So now, like what this is telling you is, cool, I give you this LQR problem. I can stack it up like this as a QP and solve a single linear system and get the exact solution. That's it. It has a closed form solution. That's pretty cool. So obviously, the whole like weird single shooting Pontryagin thing we did last time, where it took like thousands of iterations and frankly is going to barf pretty quickly because of ill conditioning. If I try to solve anything more complicated, that's a mess. This thing, one and done. I just set this linear, I solve AX equals B and I'm done and I get the exact solution, which is kind of awesome. Exact solution by solving one linear system. Exclamation point. Okay, so now we're going to go do this real quick. So back to the code. We saw, okay, this is our shooting thing. We're going to do the exact same thing now with the QP version. And the same dynamics we just saw. Same exact setup, right? 10-second horizon, start at 1. Cost weights are the same. So it's like identity on the X's, 0.1 on the R's, on the controls. Same cost, blah, 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 is all the same. Okay, and now we're going to stack up the matrices we just saw. So first, this is easy. This is that H matrix, and there's just a bunch of Q's and R's. And I'm playing a fun little trick to set that up. Has anyone seen this before? Cron, you don't know what that is? Kronecker products. So Kronecker products are great. They're super useful when you like need to build sparse matrices. What a Kronecker product is it's a product between two matrices. So like if I have A and B, what it is you take the matrix on the right and you multiply it by every scalar element of the matrix on the left. So you kind of like expand the matrix on the left. So in particular, it's great for this kind of thing. So what I did here is Kronecker product of an identity with Q and R. So what that's going to do now is it's going to take Q and R as a little block matrix, and every single element, it's going to plug it in along the diagonal. Everywhere there's a 1 in that identity, you're going to now get a full Q and R block. So that's how I'm building this like nice block sparse matrix. These are super, it's just a fun fact, like should check it out. They're super useful for this kind of stuff. It's a fun trick to play. I use them all over the place for this kind of thing. They're in all the usual places, right? That's in MATLAB too and whatever. It's called cron. If you ever see it written down, it's a circle with an X in the middle, which irritatingly is overloaded with convolution, unfortunately. So be careful there. But yeah, Kronecker products very useful. They're also, for fun fact, we'll see this maybe later, they're closely related to tensor ideas. One way to think about them is they're a way to flatten a tensor. So if you have like a 3D tensor, you can basically take the sort of, you can slice it in the third dimension and like flatten it out into a 2D matrix. And that is basically what's going on with this Kronecker thing. You can think of it that way. Okay, so that's going on. So we set up the H. I'm playing very similar tricks with the C to get all those A's and B's where I want. I'm doing like a Kronecker thingy there. The only reason this is a little complicated and I have the for loop and I don't have a clean one-liner is that first line is different, right? So the first line, I just have the B and the minus I, and then after that, I have to have the A's. So I'm doing the Kronecker trick on the B and the minus I, and then I'm going through the loop to fill in the A's because they don't nicely fit a clean like block diagonal pattern. And then the D, we already know, right? I'm putting the X naught minus AX naught in there, and then the rest are zeros. So that's the problem setup. Then I go down here. I have my KKT system like we just saw. And then I just do backslash. You know, it's like AX equals B, as easy as it gets. So I'm calling that the solution of that Y. And remember, this has on top the Z vector, which is the interleave states and controls. And on the bottom, it's the lambdas. So then I'm just over here pulling all that apart. So I'm pulling out Z, the states and controls, and then I'm kind of playing some reshaping games to pull out the X's and U's and separate them out. And then, yeah, I guess I didn't bother with the lambdas here. We don't know what those are yet. We're going to find out in a couple more lectures. Maybe after next time. We'll see. It's coming. Promise it's coming. Gotta keep you coming back for more. So, okay, so this is exactly what we saw last time, right? Same kind of solutions, pretty much the same. All that's the same. Cool. Okay, now we can play around a little bit and like maybe I can show you some fun stuff. Let's try some things. So what will happen if I crank up the R weight? Say I multiply this by 10 and like put this as 1. What do we think is going to happen to the solution? Well, there's no overshoot here at all, right? But just thinking about it intuitively, I'm putting a bigger weight on control effort. So it's going to penalize controls more. So it's going to use less control. So the U's will probably be squashed down a bit, be lower, and it's going to take me longer to like reach the goal, right? So let's try it. So keep an eye on that, right? So now, yeah, you can see it's like it's more smoothed out, and then like look at the peak here. So it's like, you know, kind of half as big or whatever. Cool. So that makes sense. Let's see. Similarly, right, if I jack up the Q weights, it's going to say, you know, get to the goal faster, right? And that all kind of makes sense. We could try that. So cool. Now here's a question. What if I jack up both Q and R by the same amount? So what if I multiply both of these by 10? What's going to happen? Let's do that. So I multiply everything by 10. What's going to happen to the solution? Have any ideas? I want to make a guess. Yeah, so that's good. Perfect. Yes. So it turns out if I do this, we can watch, right? It will not change the solution at all. So now I'm back to and in fact, this is exactly the same as the original solution we got, right? So message here is the Q's and R's on their own don't actually really matter. The only thing that matters is sort of the relative sizes of Q and R, the ratio of Q and R. And also, I mean, these are matrices, right? So the relative magnitudes of the elements inside those matrices obviously matters as well. So that's something to keep in mind for like tuning or whatever. And one way to think about this, right? Like if you took an old school CISO controls class where you're like, you know, trying to tune gains and look at like Bode plots and all that kind of stuff. Essentially, we're replacing tuning gains with tuning cost functions now, right? We're going to like play with Q's and R's to get the performance goals we want now. So it's similar in some ways, but you're kind of like operating at a bit higher level, right? Because these weights kind of are explicitly encoding goals, right, on behaviors in some sense. So it's a bit of a higher level thing. And now my iPad doesn't want to open. Okay, cool. Any questions? Anyone want to try anything? Yeah.
Do you typically just do elements of your?
You can do whatever you want. Often we use diagonal cost matrices because it's simple and easy to understand and whatever. But yeah, you can do whatever. Modulo the restriction that, you know, positive semi-definite on Q, positive definite on R. So the problem's well posed and has a solution, right? But otherwise, yeah, it's totally whatever. From a practical engineering perspective, if you're going really crazy, like putting like really weird stuff in there, you probably have something else wrong in the setup, and you probably need to like need to rethink your life priorities. It's like, yeah, usually that's a bad thing, and it should be more straightforward. Yeah. Nope. No, it'll barf. So you want to try it? Yeah. I mean, so literally the solution there is going to be infinities. What do you think about it as a linear system or as a QP? What's going to happen to that linear system? Yeah, so it's gonna have some zero eigenvalues, right? In the linear, in that A matrix and AX equals B. So what's gonna happen to that? Can I solve AX equals B then? No, right? So it's an it's an underdetermined kind of linear system, right? It doesn't the matrix is gonna be singular. It's gonna be not invertible. Here, we'll just do it so you can see. So then it literally, yeah, so the problem, like we can say it a bunch of ways, right? The problem's like ill-posed in some sense. But straight up at the end of the day, what it comes down to is that linear system is singular and not invertible. Let's see what this did. Oh, clearly that didn't do the right thing and I messed up somewhere. But anyway, that's weird. Did I regularize this somewhere? Cost constraints, solve. That's truly bizarre. Something weird's going on there. So I need to go back and look at that. Something's very wrong with that. I don't know why that happened, but it shouldn't happen. Yeah.
Stuff that we're solving when we multiply all the Q's and second, we're making it's like 10.
Yeah.
But where is the 10 getting cancelled?
Doesn't get canceled anywhere. Maybe the right way to think about it is ultimately, you know, you're solving that KK, those gradient conditions, right? So if you just like, so imagine it's a set of gradient conditions. It's a set of, it's a root finding problem, right? Where it's stuff equals 0. So if I have stuff equals 0, 10 times stuff equals 0 doesn't change anything, right? So that's maybe one way to think about it. Yeah, I need to go back and figure out why this isn't barfing. It's super, I think there's something in the code, like probably if I cleared the workspace, it's kind of bothering me now. But I feel like I shouldn't go down this rabbit hole right now, and we should probably keep trucking, but definitely weird, and we'll have to revisit that in a sec, but I don't want to do it now. So yeah, what's up?
The only thing that really matters is the ratio between the Q and the R. Is in the ratio between their values, and the Q and R matrices have exact same like array value in the diagonal.
Yeah, so I mean, also within Q and R, right? The ratios of the elements matters. In general, right, these things can be, yeah, like non-diagonal complicated matrices. The story is a bit more complicated in n dimensions. This is a scalar problem like 1D. So here it's really just the ratios, right? But yeah, in general, it's a little bit more subtle. But the meta point, like if I, is that like really these things only exist in sort of relative terms, right? If I go multiply everything by 10, it doesn't change the answer.
Like if we have X and Y one to that, get more closer to Y.
Right. Exactly. So if it's in 2D, right, there's multiple directions. You can weight the directions separately. Yeah, exactly. Yeah. That's encoding like goal kind of behavior, right? So like, yeah, it's like how much you care about reaching the goal at the last time step. So if you kind of don't care if it takes a long time to get there, you can make the stage queues small and then the terminal queue really big. So that's saying, you can take your time getting there, but you have to get there by time end. And so that can kind of, encode different behaviors, right? It's all like fairly intuitive. And honestly, if you just play around with this stuff and like you'll kind of get the hang of it. There's a bit of kind of intuition, but it's like fairly intuitive. Yeah.
So this is like a time right? The Q and R.
Yeah.
So what if we kind of oscillated every single one in the trajectory? Like
You can do whatever you want.
so like what's Q like greater than R, and the second one is R greater than Q.
Then you'll probably get some weird oscillatory behavior in the solutions. Yeah. I mean, yeah, you can do whatever you want. Like, go try it. I don't know. Yeah. Okay, cool. Yeah.
So the inverted whatever sparse matrix.
Yes.
This is not getting sparsity in that case of bad idea because the inverse will not be sparse.
So we don't ever actually invert this. You're doing something smarter. You never are computing like inv of that matrix. You could. It's a bad idea though in general. And that's exactly what we're going to do right now. So thank you for the lovely sort of foreshadowing. Okay, cool. So let's move on unless anybody has anything else. We're going to kind of dig into that matrix now and like exactly address what you just brought up. So just to kind of recap there, that example. In summary, this works much better than shooting. And you generally shouldn't do that if you can avoid it. Okay, so now we are now going to sort of take a much, much deeper dive into that QP at like a granular block level and see what's inside there. And exactly exploit the fact that this matrix is super sparse. Okay, so first off, let's do this. So we got the KKT system. Which is super sparse. And for those who, are not, hip to the lingo here, it's that means there's lots of zeros in that matrix. That it's mostly zeros. And in this case, and in a lot of cases in applications, it's not just that there's lots of zeros, it's the pattern in there of like where there are non-zeros is very structured. It's like block structured here, lots of block banded kind of stuff, stair step stuff. It's not random. In fact, random sparse matrices are evil and terrible and make your life hard. And you can't play these kind of tricks if it's random sparsity. Okay, so and has structure. And in fact, this idea of matrix structure, like sparsity patterns, goes really, really deep and is closely related. Like thinking about these sparsity patterns has deep connections to graph theory. And also like it ends up being like once you kind of get into this, you get some intuition for it. It basically reflects the physics of the problem. Like if you think about, I don't know, manipulator dynamics and like robot, topology, like the structure of the links and how they're connected directly shows up in the sparsity pattern. Here, right, the temporal structure of the control problem is directly reflected in the matrix sparsity pattern. So like, as you get more into this stuff, you'll start to like figure this out. And there's a lot of deep connections between, all these things.
Like there's more independence between things so that things get in diagonal.
It kind of, it basically, it's the question of what's coupled in the problem. So if nothing's coupled, you have a diagonal matrix. Here, everything is per time step in the cost and everything, and the only coupling across time steps happens in the dynamics constraints. And in particular, time step k and k+1 are coupled, but k is not coupled to k+2. So that means you're getting a single off diagonal element coupling like k and k+1, and then after that, nothing, right? So that's kind of the idea. It reflects coupling between things in the problem, right? In a kind of very deep sense. Okay, cool. Lots of structure. So let's draw that. So what we're gonna do now is we're gonna write out a really small LQR problem, like just like 3 or 4 time steps, and explicitly write out the matrix, and then kind of stare at it and recognize some patterns. So we're gonna kind of just deal with our problem. And maybe I'll like try to write the right-hand side vector first, so I can like make sure I keep everything lined up. So we got U1, X2, U2, X3, U3. Cool, we'll stop there, maybe X4. We'll go to 4. So X4, and then we're going to have our lambdas. So we'll have lambda 2, lambda 3, lambda 4. And this is the convention we used previously when we did Pontryagin and all that stuff, where the lambdas kind of, for the dynamics constraints, correspond to the sort of the next time step. So the first dynamics constraint where it's like ax1 plus bu1 equals x2, we're going to have that be lambda 2. So we're going to start at lambda 2 for a reason that maybe will become obvious after we start doing this a little bit. Okay, so then we've got our big matrix in here. And this is going to look like, right, we've got Q's and R's all the way down. So it starts at starts at R, sorry. It's like just what we had before. That R, Q, R, Q, R, Qn. I think I'm doing that right. Yeah, Qn or Q4 or whatever. And we're going to kind of block this out a little bit. And then down in this lower left is our dynamics stuff, right? So this is our C. So this is B minus I, then A, B minus I, A, B minus I. And then up here is just the transpose of that. So it's going to be B transpose minus I, A transpose, B transpose minus I, A transpose, B transpose minus I. Now I can, I guess, move all this over. And this is a big block of zeros right here. Cool. Okay, so we got this. I'll move this over so it lines up. And then on the right-hand side, we've got a whole bunch of zeros. And then down here, we've got that like minus a times x1 thing, and then some zeros. That's the right-hand side vector. Cool. I think I did that right. Everyone cool so far? So I'm just writing this out for like a few time steps. Okay, so now we're gonna like zoom in on this thing and actually look at it row by row. And it turns out, because of the sparsity structure here, because of the pattern in this matrix, we can actually solve this thing row by row. And does everyone remember, like from your, like, I don't know, freshman, sophomore linear algebra, doing back substitution on like triangular matrices, like forward and backward substitution on like upper and lower triangular stuff? You guys remember this? Anybody? Show of hands. Couple people. So the gist is, if I have an upper triangular matrix and it's like ax equals b, the bottom of that matrix, it's only a scalar equation, right? So I can solve the bottom row for the bottom element of x by just solving a single scalar. Then I plug that answer back in. And then the next row is like the bottom 2 elements, but I already solved the first one. So now it's another scalar equation that's easy to solve. And I can recursively go up the matrix, right? That's called back substitution. You can do the same thing if it's lower triangular, you do forward substitution. Same idea, just going the other way, top down. So we're basically going to do back substitution. So maybe go Wikipedia back substitution for upper triangular matrices as a refresher, but this is basically that idea. And in particular, if I stare at this thing, look at the bottom, I guess not the bottom row technically, but the bottom row of H. So we're going to sort of zoom in there. So we're going to look at this row. And we're gonna sort of write this out just on its own. So that row is just Qn times x4 minus lambda 4 equals 0. That's kind of nice. That's it, right? That's that whole bottom row. That's all it says. So remember, so yeah, there's a couple things you could do with this, but what we're going to do and what turns out to be useful, and this is just a reflection of the same story as the Pontryagin thing and the starting at the end for the lambdas, remember, right? We're basically doing that. So what this is telling you is that lambda 4 equals Qn times x4, which is, we already knew that, right? That was from Pontryagin. This is lambda n, like lambda at the final time. So there we got it through, this Pontryagin stuff. Here it kind of just shows up in the matrix, right? So it's kind of obvious that this should be the case based on our previous exposure to Pontryagin. So what we're going to do now is it's sort of like the backward pass from Pontryagin, but it turns out it shows up in the matrix as this nice stair-step pattern. So we start there. Now we're going to go to the next row, which is this guy. Use a different color. So this says, all right, just this row, this is R times U3 plus B transpose lambda 4. And I can now take that. I know what lambda 4 is now, right? So I'm going to plug lambda 4 into this guy. So I get R U3 plus B transpose Qn x4. So this is kind of the back substitution idea, right? I solve the bottom row, plug it back in. Now I can solve the next row. So this thing has to equal 0. And now what I'm going to do is take the dynamics constraint that says A times, so I guess technically I'm taking, a row out of the C's there. Right? I'm taking the dynamics that say AX3 plus B U3 equals X4. I'm going to plug those in for X4 here. So plug in dynamics for X4, and I'm going to get the following. RU3 plus B transpose Qn, and now instead of X4, I've got AX3 plus BU3 equals 0. So far, so good. Nothing crazy. I'm just like kind of playing games and doing back substitution. Okay, so now though, there's something cool. Okay, so look at that equation for a sec. What variables are in there? Just X3 and U3, right? So here's where something actually kind of deep and magical happens that we'll like dig into a little bit more. So from there, I can go and rearrange that line and solve explicitly for U3 as a function of X3. So let's do that. So literally all I'm doing is like moving stuff over and inverting some things. So this now tells me that U3 equals minus R plus B transpose QNB inverse B transpose QNA X3. Okay, that's a lot, but it literally, right, I just rearrange that line and solve for U3. So this is kind of wild, actually. So now it turns out I have this, well, maybe I won't spoil everything, but here we go. So there's this weird giant matrix. It's a little messy, whatever. Don't worry about it. We're going to call this thing K, capital K. So we'll call this K3. So now I have this. So we're going to introduce K. So now I have U equals minus KX. We'll come back to that in a sec. Okay, so now I'm like off and running. What I'm going to do next is we'll keep going up the matrix. I'm going to take the next row and sort of plug that in and keep trucking. Oops, need to go farther down. So now we've got that row just on its own, right, is Q3, or it's just, yeah, we're not doing that subscripty stuff because it's a pain. Qx3 minus lambda 3 plus A transpose lambda 4 equals 0. That's what that line is in the matrix, right? So now we're just going to plug in stuff we already know. So first we're going to plug in lambda 4. And we're going to get qx3 minus lambda 3 plus A transpose qn x4 equals 0. Now we're going to plug in the dynamics. Just kind of keep the party going. And we're going to get qx3 minus lambda 3 plus A transpose qn ax3 plus bu3. Okay, now we're going to plug in our previous result, which is u3 equals minus k3 times x3. And we're going to get, what that's going to do in particular is eliminate u and get it to be just in terms of x, right? We're getting rid of u, replacing it with a function of x. And what that's going to let me do is explicitly solve for lambda 3. So that's going to be lambda 3, and I'm just going to rearrange it all. This is a little messy and tedious, so, if you care, probably should go back and stare at it yourself a little bit. So this kind of mess, maybe I should. Times x3. Okay, so that's actually a very useful thing. And we're going to take this guy, this other matrix thing. Turns out we need this as well. We're going to call this P3. Okay, so now if I stare at this, I've actually now found a recursion, right? Because right now I've got lambda 3 equals P3 x3, which is exactly the same as where I started with lambda 4 equals qn x4. So I've bootstrapped a recursion by kind of like solving these 3 rows at the bottom. And now I end up back where I started, and I can do the next 3 rows and kind of just keep going up the whole matrix until I get to time step 1. Okay, so I'm going to now summarize this in like a general kind of way. Does everyone see that, right? Like basically, if I make qn pn, it's exactly the same as this. And let's just, we'll write that down. So now we have a recursion in terms of k and p. So in particular, I'm going to start the recursion off at time step n with pn equals qn. Then I'm going to solve for the k, the next k. So this is k sub k equals, and yeah, it's a little messy, and we'll see more of this, and like, you'll get more familiar with this. But for now, lots of algebra and just kind of weird matrix substitution tricks, basically back substitution though. So that's that. And then I can take that, plug the k in, and solve on the next row and solve for pk. And that's q plus A transpose pk plus 1, A minus bk sub k. Okay, and this obviously runs backwards, right, from n to 1. Okay, so this thing that I just wrote down is the famous Riccati equation, or Riccati recursion. So Riccati equation / recursion. It's worth pointing out that there's like, I don't know, at least 4 things that we call the Riccati equation. It's a little annoying. If you kind of dig in the control literature, you'll see the continuous algebraic Riccati equation, the discrete algebraic Riccati equation. Basically, there's discrete time and continuous time versions of this that look slightly different, but are almost the same. And then there's also a finite time versus infinite time. Exactly. So there's like 4 versions of this. There's discrete and continuous time, and then there's finite and infinite horizon. We're going to talk about that in a second. So, but thank you for bringing it up. Cool. Okay, Riccati. And the message here is I have this nice recursion now. So this lets me solve the QP without doing backslash on this giant matrix, and instead doing this forward-backward recursion thing. So we can solve the QP by first doing a backward pass with this Riccati thing to get Ks and Ps, followed by a forward pass where you're going to roll out the dynamics. So basically the backward pass gets you Ks and Ps and Us essentially. And the forward pass gets you the Xs. So followed by a forward, I guess in this case, yeah, roll out to impute X 1 to N. And in this case, U 1 to N minus 1. Okay, so there's lots to say about this, and we're going to kind of dig in a sec. Some first kind of notes on this thing, and like, why would I ever do this instead of just solving the QP with backslash? There's, turns out, many reasons. The first one to bring up is if I just think about this as a clever way to exploit the sparsity in that QP and solve it efficiently without like messing around with all those zeros, that actually right out the gate has a major win. So can anyone tell me the complexity of solving a linear system like big O? N cubed, right? So what's N here? It's number of time steps times the number of controls plus the number of states, right? So general, if I were to just solve the QP naively and treat it like AX equals B, like a dense matrix problem, this would have complexity of basically big O of like kind of number of time steps, big N, times number of states plus number of controls cubed, right? That's kind of the size of that matrix, where this is, right? Horizon and state dimension and control dimension. Okay, so what about this Riccati thing that we just derived? Can anyone tell me what this complexity is? Yeah.
Just basically matrices that are the size of your.
That's literally just saying, yeah, like that's just the size of the matrix, right? It's number of time steps times state plus control size, right? That's how big that matrix is, basically. So it turns out the Riccati thing we just did, the key insight here is it's got some recipe where I am solving a linear system, right? There's some inverse stuff happening in there. So we are inverting stuff. There's some cubic stuff, but we're inverting things that are like little m size. What about in time? It's linear in time, right? Because I'm doing that little 3-line block, and I just repeat that n times for n time steps. So it's the same amount of work at each time step, and I just do it n times. So it's linear now in big N. This is a huge win, it turns out. So it means now that like solving long horizon problems is not scary. It basically, if it's twice as long, it takes twice as long to solve. No big deal. And that's actually a huge, huge win. So so now it's like big N times little n plus little m cubed, roughly speaking. So it's still cubic in the state control, but in the time horizon, it's linear, which is a big win. Okay, so now that's sort of reason one to care about this. Is a big computational win. This is like basically, sparse matrix stuff. There's another really even deeper, even bigger, more important reason to do this. Okay, so we said like deterministic optimal control, the solution is an open loop trajectory, blah, blah, blah. When I solve the QP, the answer is a vector with a trajectory in it. When I solve this thing with Riccati, what do I actually get? After I solve the backward pass, I don't have a trajectory. I didn't get states and controls from the backward pass. What did I get in the backward pass? I got these Ks and Ps, right? What's that K thing? So here's the K, right? It says U equals minus KX. What's that? That's a feedback policy. So somehow by playing this like weird sparse matrix game, instead of just getting a single trajectory solution for a specific X1 that would have only been good for a single initial condition, somehow out of this like gymnastics we just did, I instead got a general feedback policy that can now give me the solution for any x1 from anywhere. And it gives me stabilizing feedback along the whole trajectory. So if I have like noise, disturbance, modeling error, I just run that feedback policy and it stabilizes and tracks and then the whole deal. That's kind of deep and kind of magical. And it's like sort of super unclear how that happened right now. So this is our second look at, or maybe third look. We're doing like LQR 3 ways. The next way will illuminate like what's up with that feedback policy thing. But for now, you should know this is like super cool and like, you know, there's some mystery in there still. Yeah.
If we solve the QP normally, that will also still have this property.
If you solve the QP on its own, it's just giving you the trajectory solution, the one-off trajectory solution, not the feedback policy, right?
Some kind of, because the solution for the Riccati and the QP is supposed to be the same thing.
So yeah, maybe let's do it. So yeah, feel free to keep bugging me with questions. I'm going to pull up the code and we'll like walk through this. And I'll kind of show you it maybe more explicitly and hopefully it'll become a little clearer. So here's the QP thing we just did. And I cleared the workspace to try to like see if this would fail, but I want to just go put it back for now. Let me like kind of set it back to where we were to start with. So it's all matching. Cool. So we're going to go run this again. Again, this is solving the QP for a single initial condition, right? And we get this solution. All good. So I'm now going to go do the Riccati version that we just derived. And we're going to sort of get the same answer first. Same stuff, right? Everything's the same. Blah, blah, blah. Costs the same. Blah, blah, blah. Okay, so here's the Riccati thing. So kind of pay attention, right? So we're going to sort of kick things off. We got our P's and K's. Pn is Qn, right? Terminal cost. And then we do this backwards recursion. So we go from n-1 to 1, and we compute k, and then we plug it in and compute p, and we just go backwards, and we get all the k's and p's. So remember, right, that k thing is actually a feedback policy that works for any x naught, right? It's the general solution. We've like solved the problem in like a deeper sense. And then in order to get the specific x's and u's for a specific x1 or a specific initial condition, which is all I got from the original, what I'm actually going to do then is do a forward rollout starting at the given initial condition. So if I do that, if I compute the feedback policy and then roll it out with a given initial condition, I will then get the same solution vector as the QP, right? Does that make sense? So here we go. So this like matches, right? But the way I got that was actually take the feedback policy and roll it out forward, right? With a given x naught. The deeper thing here is that, and right, that matches exactly, cool, whatever. So, but the deeper thing is I can now, with that k, I can start this out anywhere. So I don't have to start it at that x naught, right? I could like start it literally anywhere. So like, you know, we can like put some offset on here, roll it out again. Oh, I screwed something up, didn't I? Did that work? Or did it complain? Yeah, it worked. Okay, cool. Yeah, so, I mean, that doesn't look appreciably different, but, you know, for instance, I could, okay, maybe I subtract that. So it's actually starting on the opposite side, but you get the idea, right? Like I can take any x naught. I don't have to resolve anything. I've now got the general solution for any initial condition. And even deeper still, right? Like I can now do this with noise. So like I can start it out randomly. And in the rollout now, I'm adding random noise. So if I tried this with the open loop trajectory, it would just blow up and look stupid and wiggle around and go wherever. But now I'm adding all this noise starting in a different spot. Oh, what the hell? Oh, I screwed something up. Can anyone? I can't see over here. It's very annoying not being able to see the. Cool. So lots of whatever initial conditions, and then in particular, the important thing is here in the loop, right? I'm adding noise at every time step. So this is actually a stochastic problem now. And if I just rolled out, I guess we have to plot it up here. So you see it's wiggling around. I guess I should add more noise so it's more wiggly, so it's actually hard. But like meta point, right, is this would completely just fail, like wiggle around and look stupid in the sort of general, in the like open loop case, this would not work, right? But now I've got this feedback policy, works everywhere, works on stochastic problems, works if there's modeling error, and like deep kind of thing there, like is that, right, we did the random noise. So now, if I, yeah, we'll, okay, so probably need to stop there for a sec. There's more to say. So cool. Anyone want me to try anything else here? Yeah.
This is basically like a time varying controller. Where like
Yes.
you have to give K for every time.
That's right. Yep. That's right. You got it. Okay. So hold that thought. We're going to do that now. Okay, cool. So more to say. So we'll come back to this in a sec. More fun. Okay. So let's see. Just to kind of summarize that. So we got this Riccati thing. We did the example. So first off, the Riccati solution exactly matches the QP. But sort of bigger deal is that the feedback policy lets us change the X naught.
And I think when you solve the QP, you don't explicitly find the relation between.
That's right. You don't, you just get an open loop solution, right? That just gives you a trajectory. So now we can change X naught and we can sort of do disturbance rejection and stabilize. That's kind of deep. Okay, so anything else on this before we keep trucking? Yeah.
Oh, so like for K's are and like for P's are giving lambda. Saying,
Hold that thought. Yeah, we're going to do that for sure. And we'll do explicitly tell you what the lambda situation is. But yeah, not quite yet. We're going to need a little more stuff for that. Okay, so now what I'm going to tell you about, which was kind of floating around in the air just a second ago, is this idea called infinite horizon LQR. Okay, and so probably I should pull back the code notebook for a sec to get at this, just as a kind of teaser. So what I'm going to do here is, remember K, it's a 1D dynamics, so it's a 2D state. So it's position velocity, and the feedback Ks, they're multiplied, they use a scalar. So K is just 2 elements. It's a 2-element row vector. So what I'm going to do here is plot those 2 K values as a function of time. So remember, we start at N and go to the beginning. And this is what that looks like as a function of time. So interestingly, right, it starts over here. So as we go backwards, it's changing, but then pretty quickly, remember, this is like 10 seconds, right? So after about a second or two, it's converging to these steady state values and it stops changing. That's kind of interesting. So what's going on there? So this is this idea called infinite horizon LQR. And so the idea is, for a time invariant problem, i.e. the A's and the B's and the Q's and R's are not functions of K, they're just constants. So for time invariant, it turns out that both the P's and the K's converge to steady state values as you go backward in time. And they actually generally converge pretty quickly. And so for stabilization problems, so i.e. we have some equilibrium point that we're just trying to park at and stay there. So this is really ultimately, like when we talk about time invariant versus time varying LQR, time invariant generally means stabilization problem, like you're trying to keep it in one spot. Time varying LQR generally corresponds to tracking problems. You're trying to track a trajectory over time. That's kind of how those two come up. So for these kind of stabilization problems, we generally just use what's called the infinite horizon LQR solution. So that single K, we generally don't bother with the time varying K. We just take that out till it sort of steady states, and then we just take that fixed K. And so the idea is, if I like remember that backward recursion stuff, I can sort of solve that directly for the steady state value. Does anyone know how to do that? Yeah, exactly. So I could just iterate it for a while, right? I could iterate it like 100 times, 1,000 times, whatever, and it would steady state, and that's cool. You could do that. Or you can sort of look at this guy, right? Which we sort of know now. So it's K, blah, blah, blah. Yeah, this is annoying to write. Okay, so there's K, there's P. And in these equations, right, I've got PK plus 1 and P both, right? And so the key insight is if I just set those equal, so this infinite horizon limit means that it's no longer changing. So I can set pk plus 1 equal to pk equals this kind of p infinity. And then I got a set of equations directly in terms of that p infinity that I can just directly solve. And so in particular, right now, if I do that, I end up with like a root finding or fixed point problem that we know how to solve, right? Newton, whatever. It turns out that shows up. You could just do Newton on that, and that's totally fine. It turns out this shows up often enough and is an important enough thing that people have developed specialized solvers for it. You should use those instead of doing it yourself because they're more efficient and numerically better. And in particular, this is in sort of in all the things, right? Julia, MATLAB, Python, whatever, all the sort of standard toolboxes for this is called DARE for discrete algebraic Riccati equation. So yeah, you should just use that. Okay, so maybe we should take a look at that real quick. So here's our infinite horizon. So basically, we did Riccati and we saw that it flatlined out here. So what I'm going to do now is use the toolbox. So in Julia, and it's exactly the same in MATLAB. There's a function. So DARE will give you the P, and then this other function DLQR, which stands for discrete time LQR, will give you the K. So I just give it the ABQR, and we're going to compute it here, and then we're going to spit out R time step 1K, right? And we'll look at those. And they, I subtract them. They match to like, 1e minus 9. So they match like 9, 10 decimal places. So they're the same. And then the last thing to show is, right, again, I'm going to now just roll it out with the fixed K instead of the whole time varying K thing. And I guess now we have to back up and look over here again. But yeah, you basically get the same answer, right? And in particular, right, remember, it's constant all over here where the action is. It sort of only changes over here at the tail. So you're already at 0. So it literally gives you almost exactly the same solution. Yeah, so there's that. Last thing to mention about this is if I go plug in that K, my closed loop system now it's an autonomous system again. So if AX plus BU, I plug in U equals minus KX. Now what I have is A minus BK times X, right, is my new dynamics, and that's my new closed loop A. So if I go look at the eigenvalues of that new closed loop, this is discrete time, remember, right? So remember, what is stable in discrete time? Norm less than 1, right? So there's my eigenvalues. They're both less than 1. This is a stable closed loop system. So the last kind of takeaway point is if you've ever done like old school SISO control, and you remember you had to play a lot of games with tuning gains and then checking like gain margins, phase margins, blah, 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 to make sure that the closed loop system was stable, right? So it turns out if you do LQR, you're guaranteed, as long as it works, right? As long as you're sort of setting the problem up properly and, blah, 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 you're guaranteed to get a stable closed loop, at least on the linear system that you plugged in, right? Modulo modeling errors and everything else, right? And this is, we talked about the famous sort of, LQG, phase and gain margins, stability margins, there are none, right, from Doyle. So that's with a Kalman filter, with a state estimator hooked together. If you're doing full state feedback, just LQR with no state estimator, these guarantees are there. So you're guaranteed to get a stable closed loop that's actually pretty robust. There's actually robustness margins on it. It's when you hook it up to a Kalman filter that it can go off the rails. Okay, cool. Any questions about this stuff? Yeah.
Like you said, our control is like no longer perfectly optimal, it's just pretty good. Is that also the case if before we were changing our X0? So like if we were starting it.
So no, yeah, that is the optimal feedback policy. That is the optimal. That is the best you can do. So literally for an LQR problem, if you have linear dynamics and a quadratic cost, this is the answer. Like there's nothing better. So that's kind of a cool thing. And that's why this is such a deep thing. Like for this kind of problem class, you can get the optimal answer. You can get the optimal feedback policy. You've solved everything. Like that's all there is, right? You can't do any better. That's all, right? Which is a very, very deep and cool thing. And it means in particular, right, because we went back to this whole argument, if you have a smooth problem, like if everything in your problem, if you're solving an optimal control problem, if everything's differentiable, right? If you can take nice, if it's nice and smooth, cost function, dynamics, blah, blah, blah. If I locally Taylor approximate the whole problem, I get an LQR problem. So what that's really telling you, which is a really deep result, actually, if you're doing, for example, if you solved some big nonlinear problem, you got a trajectory, the locally, if you're close to the reference, if things are on the rails and working, you're not getting super knocked around, doing reference tracking with LQR is locally optimal. It's a local approximation of the optimal policy, which is really deep, right? So like what that's really saying is like, if I find a nice trajectory for a crazy nonlinear system, and then I linearize around it and do LQR, that as long as I don't get knocked too hard, that's optimal. That's basically optimal for some small epsilon perturbation, right? Which is super cool. Okay, guys, I think that's about it for today. More next time.